Okay, I think we should start. Welcome to everybody to this plenary session. And we're going to have 3 different speakers about different subjects. It's a pity that our 4th speaker, Mirjana Povic, cannot do it today. I mean, we wish her just a very quick recovery. And okay, we are going to cover 3 different subjects. And our first invited speaker is Beatriz Sánchez Cano from the University of Leicester. And she's going to talk about the star-planet interaction, a journey through the solar system. Okay, Beatriz, the floor is yours.
Yeah, thank you, and good afternoon, everyone. Thank you so much for being here today in this talk. And I just wanted first to thank everyone in the committee for inviting me to come here. It's actually quite emotional for me because I remember my first ever talk in a conference was many years ago in this Congress. At that time, it was in Madrid. It was in the CSIC main place. But it has been quite emotional to come here after living for so long in the UK. And I have a very big responsibility, actually, because when the committee told me to talk about the star-planet interaction, so it's actually a very big topic, and it can be seen from many perspectives, from planetary science, like is my case, but also from astrophysics and astronomy point of view. But I thought I could invite you today to come with me for, like, let's say, 20-25 minutes of a journey in our solar system and understanding how is this interaction of each planet that we have nearby us with our sun, and let's see what we can learn and how we can compare the interactions between them and what we can learn that can be applicable for other planets outside our solar system. So with that, I will start my presentation, and I know this is just a very particular planet, so this is Mars, but I wanted to show an example of why it's really important to study the evolution and understanding the interaction of the sun with the planets. And I think the most dramatic case that we have in the solar system is Mars. You can see on the left a figure of Mars now. It's quite dry, no water at the surface. Well, there is ice and so on, but no liquid water. But on the right, so we have a picture of Mars in the past. Of course, it's not a picture, it's a recreation, but we have thousands of evidence that show that in the past there were abundant water at the surface of Mars. So this is for being 1 week here. That's why I mix Spanish and English, sorry for that. So we know this happens. So the key in here is understanding the interaction of Mars with the solar wind, with the sun, and it's a key for understanding planetary evolution. But it's not just Mars, it's actually all the planets. No worries, I'm not going to go through all the details in the figure on the right of the slide, but this is a very nice summary of atmospheric escape processes that happens in many planets in our solar system, including Earth, Venus, Mars, and comets in this picture. But you can see even Earth has a very abundant amount of atmospheric escape every single day. So we need to understand that because this is the key for understanding the evolution of the planets, but also is the key for understanding the planetary habitability. And habitability is really a big name nowadays in our field. And for that, I put this kind of a sketch on the right of the slide, which I like very much because this sketch can be applicable to any body. And maybe, depending on the body, you will have different blocks. But in reality, any planet can be, or any body in the solar system and beyond the solar system can be reproduced with this scheme, where you have, on the right, you have the neutral part of the atmosphere. On the left, you have the ionized part of the atmosphere. You have the arrows. Hopefully, I can show. Okay, no, maybe not. You have the arrows that came from the sun, which is the flux of energy moving into the system, and the connections between the layers. And you see on the top left, there is an interaction with the solar wind, and there are 2 types of interactions, and this is what I'm going to talk today. Depending on the magnetic configuration of the body, we will have a different interaction. So why to study our solar system? Because actually it's amazing. I mean, we have a very natural laboratory next to us, and we can actually go there and explore in situ. So we have bodies with atmospheres and magnetic field, as you can see here, Earth and all the giant planets. We have bodies with atmosphere, but no magnetic field, or almost no magnetic field, like Mars, Venus, or comets. We have bodies with no atmosphere, but magnetic field, like Mercury, which is now quite interesting because of Bepi Colombo. And also we have other bodies that they don't have atmosphere and they don't have magnetic field, or almost they don't have magnetic field, like the moon and the asteroids. But even more, we have another set of magnific bodies we can have everything, can have or not magnetic field, can have or not atmosphere, but they are within subsystems, especially in the giant planets. This is amazing because we have like basically all our laboratories there, just next to us that we can go and explore. And moreover, because we are talking in here, we are going through all the solar system with this interaction with the solar wind, the main manifestation of that is the aurora. So we know for sure we have aurora at Earth. Even hopefully in May you were able to see the auroras here in Spain. But also we have the massive auroras in the giant planets like Jupiter and Saturn. But you may not know that other planets like Mars has tons of auroras, like really tons of auroras everywhere on the planet. There are moons like Ganymede, which has amazing aurora. It's a moon, and it has auroras, and it's inside a system. It's inside Jupiter. So Jupiter has auroras, Ganymede has auroras, so imagine the interaction going on in here. And there are planets like Mercury with no atmosphere, so where the auroras came from? So the auroras came from the surface. We will see that later particles precipitate in the surface and produce emission of X-rays, which are considered kind of aurora. But how we are going to study this? So first, we need to understand what happened with our sun. So our sun is amazing. Okay, it's very small compared to all what we have been seeing this week in here, but it's actually amazing. So we have, depending on in here we have different filters to observe the different levels of activity that we use every day. I'm not going to go into all the details, but what I just wanted to let you know, which is important in this talk, is we know the sun can be considered as a black body, but only for wavelengths larger than ultraviolet. So if we go to the to the left part of the graphic, so we have the extreme ultraviolet and the X-rays, especially the soft X-rays, which are the most important for us because they create ionization in the atmosphere. So why I'm saying this? Because for any single body in our solar system and beyond our solar system, so if the body is nearby the star or close enough to the star and has a neutral envelope, it will have an ionosphere. And the ionosphere is the upper part of the atmosphere that is ionized because the sun or the star in particular send photons that ionize this upper part of the atmosphere, producing the ionosphere. And because the ionosphere is created because of the neutral atmosphere, is very responsive to what happened in the neutral atmosphere, as we will see later. But at the same time, because it's an ionized layer, so it's responsive to electric field and magnetic field. So it's an amazing layer that is everywhere in all the systems and really controls all the evolution of the planet. But if I'm back to the sun, so we have other features in the sun which are very important in our particular sun in the solar system. So our sun has a different rotation that you know. So that produces that particles rotate with the planet and also with the sun, and they escape the sun, and they escape and basically fill all interplanetary medium, which is what we call the solar wind. But the solar wind is frozen in, which sounds very weird, but it's actually an amazing property that we have. So this means the plasma from the sun moves with a magnetic field line from the sun, and they never merge with another one. So this is what you have on the figure on the right. Imagine that we are looking to the sun from above the ecliptic, so we have all the solar system below us, the sun in the middle, and you see all these lines that are like kind of spiral, so this is the Parker spiral. So they move according to the rotation of the sun, hit all the planets, but they never merge between them. And if they merge, I will show you later what happens. So when one of these lines hit a planet with a lot of particles in there, this is what happens. So this is an animation of Mars, because I thought it would be easier to show Mars because there is no magnetic field on that. So we have the solar wind coming from the right of the slide at super Alfvénic speeds, so 500 kilometers per second on average. It could be even 1,000 kilometers or even more. It hit the planet, and when it hit the planet, so the velocity reduced drastically because it encountered the plasma from the planet. And then this is what we see, a deceleration in particles, and then a magnetosphere is created. So these are observations actually from MAVEN at Mars, but we have this for every single planet. And this is a magnetosphere, but what is actually a magnetosphere? So let's go to a classic view. So this is Earth, because Earth is a planet, even if sometimes we forget, especially in planetary conference or astronomy conference. So we have an incredible planet, which is Earth. And this is the magnetosphere. Actually, is our home in space. So everything that is inside the magnetosphere belongs to the planet. And as you can see in here, so we have at Earth a dipole. And this dipole is kind of degenerated towards the night side. So the sun, the solar wind is coming from the left, your left, yes, is coming, and is because of the pressure that is exerting on the magnetosphere, it deformates the lines, and then it elongates on the night side. But you see there are two colors. There are red and blue. So this is because in the subsolar point, we have something called magnetic reconnection. So this is when two magnetic field lines that never, ever merge, so we have the sun and we have the Earth lines, but when they have different orientations, so they can actually reconnect, and then in that case, we have an open line. So this open line is connected to the sun and connected to the planet at the same time, and are the blue ones in there. So this is what is called the DESY cycle, and it creates the auroras. I'm not going to go into all the details, but you can see the sketch at the bottom right of the figure on the left, that this yellow band is actually the auroral oval that we have at Earth. And on the right, there is a simulation, because this is a quite live process that happens every hour. Every hour, we have a magnetic field line moving from day to the night side, producing aurora. And this is actually what happens in a normal day with normal conditions. So it's a quite dynamic motion. So this is Earth's magnetosphere, but what happened with other planets? So I like very much this sketch because it gives you, in a quick view, the size that we have in our solar system. Earth, even if we live there and it's amazing, it's actually a quite average planet. But it's not average compared to Mercury that you can see on the top left, because Mercury is very small, so we have the same kind of magnetosphere, but very, very small, because the magnetic field is only 300 nanotesla, while at Earth we have 50,000 nanotesla. But then we have the massive planets like Jupiter, Saturn, here at the bottom right. We have a massive structured magnetosphere. With they are very large, for example, Jupiter magnetosphere is the largest object in our solar system. But however, when you compare to the scale of the heliosphere, because the heliosphere it's also a magnetosphere. So you have on the bottom left of the slide, so it's actually large, but it's not, of course, not as large as the heliosphere. But you can clearly see the interaction with the interstellar medium, that this, again, there is a bow shock and there is a magnetosphere created by the sun. So this is the kind of structure that we are having a look today. So I'm going to start from closer to the sun to move outside to the sun, to the solar system, and I'm going to start with Mercury. So this picture that you can see there is a real picture taken by Bepi Colombo 2 years ago during the second flyby. So you know Bepi Colombo is arriving to Mercury. Hopefully, it will arrive at the end of next year. But meanwhile, we are doing some flybys, and this is one of the pictures taken from one of the flybys. And we have, on the top of the left of the figure, so you can see the magnetosphere of Mercury, very similar to the magnetosphere of Earth, very similar to the figure that I showed before. But on the bottom corner, on the left, so you see the magnetosphere is actually slightly different. So depending on the orientation of the magnetic field from the sun, which we call the interplanetary magnetic field, so we have actually a very dynamic magnetosphere. The structure of all the field from the planet changed drastically, and then, because there is no atmosphere, the surface properties change as well. So Mercury magnetic field is only 1% of magnetic field of Earth, very small, but it's a very highly dynamic magnetosphere. I said before, the DESY cycle at Earth is just 1 hour, but on Mercury is 1 minute, between 1 and 3 minutes. So imagine when you take observations from a spacecraft, if you are familiar with that, 1 minute is nothing. Sometimes the resolution is that from some instruments. So it means that we need extremely precise instrumentation to be able to measure the dynamics of the magnetosphere of Mercury, even if it's a very small magnetosphere. And of course, it's populated for many particles from the solar wind, if you look at the magnetosphere, but this is just simply because of this massive interaction with the sun. This is a confidential figure, but I thought I will show you. So this is a work that we are working at the moment on Bepi Colombo. It's from the third flyby to Mercury, and it's the first time we see, so on the figure on the left, no worries for people not familiar, so these are energetic particles. But if you see the bottom two panels, so there is an increase, at the closest approach, an increase of energetic particles of 100 kiloelectron volts. So this is actually the first time that this is observed at Mercury. We believe it may be the ring current, but we are doing a lot of work on that at the moment with simulations and so on. But I said before that there were auroras at the surface of Mercury. These auroras came for particles precipitating and heating the surface and producing X-rays at the surface, which is the figure on the right. And we believe there is a link between the figure on the left and the figure on the right, but we have to demonstrate that. So this is really work ongoing at the moment, and it's only with flybys. So let's see what happened when Bepi Colombo actually arrived to the planet. So if we move now a bit farther, so we go now to the two big unmagnetized planets of our solar system, or I would like to say what originally people said unmagnetized, because I don't think this is actually the right name in particular for Mars. So this is a comparison. On the left is Earth magnetosphere. On the right is the magnetosphere of Mars, but actually is the same for, a priori is the same for Venus. So the scale is not the same of both figures, but you can see that the interaction with Mars, it happens much closer to the planet than with Earth. So this is simply because there is not a global magnetic field in the planet, so therefore the own atmosphere and ionosphere is the one touching the solar wind and interacting with the solar wind. So there is a direct coupling between the solar wind and the planet itself, the atmosphere. That's why the evolution of the atmosphere is more dramatic than in another planet. While at Earth, this is indirect because of the magnetic field. So for Venus, this definition is fine. Venus is quite a well-behaved planet, but Mars is not, because we have some crustal magnetic fields from the own rock. So this is magnetic field that was recorded billions of years ago, and it's still in the rocks, and it's actually, these fields are more intense than the magnetic field of Mercury. So imagine the level of magnetic field in here. So these fields actually can reconnect with the solar wind and produce a hybrid magnetosphere, and we will see that in a few slides. But there is something else. So Mars has a very elliptical orbit. So together with Mercury, they are the most elliptical orbits in the solar system, and this has an effect on the planet itself. So the interaction happens with the ionosphere, but because of this distance, the amount of photoionization that reaches, or the amount of irradiance from the sun that reaches Mars, it varies with time. So you see on the figure on the right, in green, this is the solar cycle measured at Earth. And in red, so you see the solar cycle extrapolated to Mars distance. So this is actually what you see at Mars. You see a sinusoidal variability, which is the effect of the own orbit. And when you look to the ionosphere, so on the figure at the bottom, so this is the total amount of electrons that we have in the ionosphere. So you can clearly see the same variability. So the ionosphere has this variability, and as a consequence, all the boundaries of the system, so for example, on the top panel now, we have the bow shock, which is the most external boundary on the figure on the left, so the first one that we saw in the previous slides. So it follows exactly the same variability. So this is a unique characteristic of a magnetized planet that for sure is not seen on planets with intrinsic magnetic field as Earth. So basically, the sun, the solar irradiance, is the factor controlling all the system. So this is very important, of course, when considering atmospheric escape, etc. But as I said before, Mars has strong crustal fields at the surface. So this is the map of the location where they are. So they are mainly in the south hemisphere. So these are the red, where the red colors are is the most intense magnetic fields. So you see the scale, like in orbital scales, is 700 nanotesla, so much more than for sure than Mercury. And this is one of my favorite figures. So what happened in the ionosphere? So actually, when you look to the total amount of electrons that you have in the ionosphere, to me, it's amazing. I can clearly see the magnetic fields there in the ionosphere. So there is a lot of modulations that we need to take into account when considering this planet. And this is more important because I said before there are tons of auroras at Mars. You may not know that, but actually there is a high probability for the astronauts to see auroras everywhere on the planet. So we know there are discrete aurora, same as Earth, but on the crustal fields. We know there are diffuse aurora, which are produced when there are showers of energetic particles from the sun, so the full planet glow. It's like a full illumination, full green planet. And then we know also there are auroras on the day side. They are also at Earth, but at Mars, they are very seasonal effects, which are the proton aurora. But moreover, since last year or 2 years ago, so we know that actually there are more types of aurora that we didn't know before. So thanks to the Emirates mission that is on Mars since a few years ago, so we have detected this kind of auroras that you can see there on the figure on the right. So this is on the north hemisphere of Mars, far away from where the crustal fields are, and you see the kind of feature, sinusoidal feature that you can see there. So this is what we call the sinusoidal aurora, which is basically a discrete aurora, but far away from the crustal fields. So there is no explanation to that. It's not related to what happened at the surface, but it's related to what happened at the tail of Mars. And this is a unique feature of this planet. So this is a cartoon that explains very well what is going on. On the left is the well-behaved Venus, just the magnetic field from the sun draping and creating a magnetosphere. On the right, Mars, still with magnetic field draping from the sun, but because all the crustal fields, so they interact between them, they interact with the solar wind, and then they produce a kind of party of fields in the night side, and we have an amazing ionosphere, and we have an amazing aurora observations thanks to all these fields in the tail of Mars. So that's all for Mars, but I could not finish because you may know, like, my involvement in the mission at the moment. So the future of Mars is really 2 spacecraft at least there, because we cannot do science without that. That's why there is a mission at the moment from NASA, a very small mission called Exascale that is going to be launched this year. But also, I'm proposing together with a very large, amazing team in Europe, we are proposing the mission EMMATIS to the European Space Agency, which is at the moment in phase A in the competition, only and exclusively to resolve this problem. But enough about Mars. So we move now a bit further. So what happened with comets? I will go a bit quick here because this interaction is actually very similar to Earth and Mars, sorry, to Mars and Venus. They don't have magnetic field in principle, at least the ones that we have studied, they don't have magnetic field, but they have massive atmospheres. So you know when they arrive close to the sun, they start to develop the coma, they start to develop the tail, so they have a dust tail and they have an ion tail. And this is what we see in the evolution of the periapsis of the orbits through the sun. Their interaction with the sun is exactly the same as Mars and Venus, so we typically compare, but there are 2 main differences. So there is not atmospheric circulation, which is very important when studying the ionosphere of the comet, and also the gravity is very small, typically because they are just rocks in space. So this means that the boson and the magnetosphere are much massive than they are, for example, with Venus and Mars. But the interaction is the same, but I just wanted to show at least one slide just to show you, like, we don't forget the minor bodies in the solar system. And there is also another body nearby us, is our moon, which also has a very peculiar interaction, very different to everything that I showed before. So you know, because of the orbit moon, so the orbit of the moon, so for part of the orbit is inside our magnetosphere. But when it's outside the magnetosphere, so it has a peculiar interaction with the solar wind, and this is because there is no atmosphere, so the particles hit the surface directly, and most of the composition of the surface is actually affected because of these particles sputtering on the surface. And we have a kind of wake behind the planet, and this is simply because of the interaction, so the solar wind is draping through the moon and basically hugging the moon. But also, same as Mars, but less intense, the moon has crustal magnetic fields at the surface. And there are kind of mini magnetospheres happening in the surface of the moon. Much less, weaker than at Mars, but they are still there. And they have also the same kind of interaction locally that Mars has with the solar wind. But now I'll go to the giant planets. So this is literally another world. So this is something totally different. It's actually, to me, I think is really amazing how all the subsystems behave together. So I want to start with Jupiter, but I said before, if you remember, that the magnetosphere of Jupiter is actually the biggest object in our solar system. Unfortunately, we cannot see the magnetosphere because it's just transparent, the plasma is not visible. But if this is a picture actually that you can find on the ESA website. So if the magnetosphere of Jupiter were visible, so this is how big it will look like. So, and Jupiter is at 5 astronomical units of distance, so it's really far away. But this is how big it is, that even we could see that with our naked eyes if it was visible. So it's a massive structure. Same when looking to the scheme, it's very similar to Earth, but just bigger. It has 20,000 more times magnetic field, so of course it's bigger, it's massive. That's why the radiation environment at Jupiter is so big. But also, you can see that there's a kind of deformation. So there is something in the middle that is a kind of deformation. So the lines, the magnetic field lines, are not as circular as they were for Earth or for Mercury. So also, it's very big because the solar wind is 5 astronomical units, so the solar wind is weaker there. So this means that it only feels 4% of the pressure that Earth feels. But also, it rotates very quickly. So that's why there are big auroras, because the magnetosphere rotates, so the planet rotates very quickly, the magnetosphere as well, and then the particles trapped in the magnetic field lines, they precipitate quicker to the atmosphere. So that's why the auroras are so bright at Jupiter and the same at Saturn. But this is actually when we do a close view of the planet, so this is actually what is going on. So that's why the magnetic field lines are deformated, because the moons, the Galilean moons, are interacting with the magnetosphere in very complex ways that we are going to see now with a simulation. But the main moon is Io or Io, depending on how you want to call that. But Io is a volcanic moon, and it shows it ejects a lot of material into the magnetosphere. And this material became trapped by the magnetosphere, and it forms a torus of plasma surrounding Jupiter. There is another moon, which to me is my favorite, and is Ganymede, and it's my favorite because it has a magnetic field. But moreover, we know there is an ocean below the surface, and the ocean is conductive, so it creates also a magnetic field. This magnetic field creates auroras, but at the same time, it's connected to the magnetic field of Jupiter. So I think it's the most complex interaction in the solar system. The moon itself is great. It's bigger than Mercury. It's the largest moon in the solar system, and the interaction itself it makes an amazing world to study. And actually, this is one of the main objectives of the JUICE mission, as you will see in the next slide. So this is actually a simulation that the JUICE team provided me for the presentation. So you can see Jupiter, and we are going to see the 4 Galilean moons. So the most external one is Callisto, which has also some interaction, but this is the one that we know the least at the moment. But then you will see Ganymedes appearing a bit closer to Jupiter, and then you will see the interaction of the own magnetic field from the moon with the own magnetic field from Jupiter, and the creation of auroras at both planets, the planet and the moon. Actually, it will be amazing to me as a scientist, it will be amazing to understand if both auroras are produced at the same time and what is the connection between them. Then we have Europa, which is one of the most peculiar moons in the solar system, one that is there is highly probability to find habitability or conditions for habitability. And then we have Io, which is the moon that I said before, that you will see ejects all the particles from the surface that go to the magnetosphere and creates the torus surrounding the planet of the moon. So I will go a bit quickly because I think it's already time to finish. Saturn is very similar, so I'm not going to go into all the details. Saturn, instead of Io, it has Enceladus, but it's the same process, very similar. And actually, the next L4 mission, the selected by ESA, is to go to study this moon and interaction with Saturn. But also, there is another moon very interesting in there, which is Titan. So Titan, in principle, is inside the magnetosphere of Saturn. And it doesn't have magnetic field, and it's interacting with the planet just in a kind of, subsonic way, because it's inside the magnetosphere. But from time to time, you can see with the circle, it goes outside the solar system, outside of Saturn's system. So this is because there is something in the solar wind, like high pressure, that presses the magnetosphere, and the moon can go outside. So in these conditions, which has been one time only observed by Cassini, and it was on the 1st of December of 2013. So it passed from the figure on the top, which is the normal way in which it interacts with two winds. So imagine you are in your car, and you go against the wind, and you have the separation of winds. So this is the normal interaction. But it went, during that time, outside the system of Saturn, so it went to the figure at the bottom. So basically, it went to be like Mars or Venus, just in the pristine solar wind. And this is my last slide, I promise, so I'm just finishing here. I want to just say very briefly, so we don't know much about the farther planets, Uranus and Neptune, but we know they have a very funny rotation, as you may know. And because of that, even if the magnetosphere is expected to be similar, because of that, so we know it's going to be very difficult to understand, because this rotation of the axis of the planet with the magnetosphere is going to create an elliptical structure, which I don't have any idea at all of how the plasma is going to move in here, but we really need a mission to go there to understand this. So to me, the take-home message from my talk today is like, we really have a unique solar system. It's a natural laboratory and it's there for all of us to go and explore. There is a high, intense link between planetary and heliophysics, and this is very, very important for understanding the habitability of a planet. But also, it's the same for any exoplanet. So we have kind of all planets here. I'm sure there is much more worlds with different conditions outside our solar system. So we have to understand pretty well our solar system to be able to compare and understand processes beyond. And then this is what I just said. So it's very important for understanding planetary evolution and habitability. And for sure, we don't have enough missions. So we really need more missions because the mysteries that we have just in our neighbors' planets are still unresolved, and we even don't know, I will say, 1% of all what they can show to us. So yeah, thank you very much again for your time.
Okay, thanks a lot for this very nice talk, really. I am sure there will be questions. Okay, who wants to start there, please?
Thank you for the talk. I was wondering whether you can learn about the internal core structure of the moons and planets due to the magnetic fields.
Oh, definitely. Like, for sure, this is one of the goals of Bepi Colombo. So Bepi Colombo has a very complete suite of instruments for surface and gravity and everything. But by understanding what happened in the magnetosphere, because we know the magnetosphere is connected directly to the surface, we can understand if there are telluric currents inside, we can understand about the structure, internal structure of the planet. And the same happened with other planets, like, for example, on the mission that I'm proposing to ESA, we have 2 spacecraft. So with that, we can actually do, for the first time, understanding if there are currents induced in Mars' surface, because we have 2 magnetometers that can go information and study the currents. So there is a lot of possibilities that can be done, and I'm sure it's the same with the giant planets, for sure, because thanks to the magnetic field, we know they have oceans under the surface. So for sure, you can learn about the planet itself and the system itself just by studying the interaction with the solar wind.
Any other question? We cannot see anything from here.
It's like totally blind.
Okay. Let me ask you. Yes, I was impressed with the results you saw also by Bepi Colombo with this flyby. Really, can you give more details? And then what do you think that we will be able to be observed when Bepi Colombo is already working?
Yeah, it's actually amazing because it's just a flyby and everything happens very quickly, I have to say. But it's because previously it was only properly studied by MESSENGER, and the orbit of MESSENGER cannot map very well the magnetosphere. So only with the flyby, it passed by areas that it was not explored before, so that's why we could see these particles. And we think it's the ring current of the magnetosphere, which I did not explain today because it's a lot of features in there, but it's basically the particles moving surrounding the planet in the magnetosphere. And it's very difficult to prove because with the flyby, it's just all the instruments at once taken, and at the moment, the 2 spacecraft are together. But once they separate, it will be great because then we will have one spacecraft monitoring the solar wind and the other one monitoring the magnetosphere. So then we could actually do comparisons in 2 different points of the system. But at the moment with the flyby is what we have. So we do science, but not magic, basically.
No, but you can do science already.
Oh, yes,
That is
yes.
very, very amazing. Okay, thanks a lot, Beatriz. You know that this summer we have beautiful auroras here in Calar Alto even. There are very nice pictures. If you want to go to the webpage of the Calar Alto Observatory, you could see the images of the auroras. Okay, thanks a lot.
Thank you.
Okay, and our next speaker is Emma de Oña. She's here, ready. Welcome, Emma. And she's going to talk about galactic outflows in the gamma ray regime. Emma de Oña is coming from DESY, okay? And Emma will let you know after 23 minutes, okay? And good, go ahead. The floor is yours.
Hola. Okay, thanks a lot, and thanks to the organizer for inviting me to give this talk. This is really important for us, the gamma ray community, to be here in the presence of the astronomical community in Spain, especially because next year we're going to have the most sensitive instrument in gamma rays in Cherenkov telescope. And my goal in this talk is to convince you that we're doing really great science, and you can join us and we can do things together. But today I'm going to focus on galactic physics, and in particular galactic outflows. And I want to start with this picture that probably makes you feel more comfortable with, which is the sky in the optical light curve. And here you see the galactic plane. Do we have a pointer? Yeah. It doesn't really work, right? Okay, that's better. So here we have the galactic, you can see the galactic plane, everything looks kind of peaceful, but if you go higher in energies, or shorter in wavelengths, then we go to the X-rays. This is one of the first images Rosita published in the 0.3 to 2.3 keV. And then you start seeing that there is a lot of high energy photons and very energetic things happening in the galaxy, including outflows of very, very large sizes. So we can even move to the higher energies, and now we move into the gamma ray regime, which is defined as energies beyond 100 mega electron volts. And this is the sky as is seen by by the Fermi-LAT the telescope between 10 and 500 gigaelectron-volts. And what you see here basically is the galactic plane is dominated by a fog of gamma rays, kind of diffuse emission that actually is on top of everything that we see there. We can go even higher energies in the TV regime. This is a combined, This is a combined image made out of two instruments based on two different techniques to the Cherenkov light, with HESS and LASO. There's one of the detectors in LASO between 1 and 25 teraelectron volts. And what we start seeing is that this fog disappears, this diffuse away, and then what we see is the emission of the individual gamma ray sources, the individual of each of the accelerator or the emitter of this very high energy radiation that we observe. And this is actually the range of energy in which I'm going to be speaking about. You can even go a bit higher, even at 100 TeV, beyond 100 TeV, and this is what we call the PV regime, and this is 10 to the 15 electron volt, and this is really extreme accelerators. And here, even, this is very recent results by the LASO experiment, and then you see that even at these energies, we even have more than 50 sources, which is still bright up to PV energies. So this is really outbreaking. And well, how do we reach its energies? Now I have to introduce very quick the HELAS plot. There is no gamma ray talk without the HELAS plot. And this is very simple and very powerful way to understand what kind of population, what kind of sources can accelerate gamma rays. And here basically what we have is the magnetic field and the size for a given outflow speed. And this is a very, very basic concept. It means you need to accelerate the maximum energy you can reach. You can balance. You can look by balance the time you need to reach. The time you need to accelerate a particle in a given electromagnetic field before they. Sorry. Okay. So basically, you need to accelerate the particles to certain energies before they escape the source you have. So basically, you put these two things together, and that gives you the maximum energy you can reach in a source with a given outflow velocity, with a given size, and with a given magnetic field. And this is very simple. This is a necessary. That doesn't mean you're going to have gamma rays, but this is a necessary condition to really reach these energies. So you can just get all the population of galactic sources and put it here for typical magnetic fields at typical size, and then you see if you can actually go and accelerate. This is a line for 1 PV for the speed of light, and it tells you if you can actually reach TeV, PV energies in these objects. And then you can have things like neutron stars, which are very small, we have like at the order of kilometers, into the 3 kilometers, and then but this you have extremely high magnetic field. So you are actually here. So that means potentially you can accelerate particles to this maximum energy and create and produce gamma rays. And then you have things like supernova remnants or pulsar nebulae or stellar clusters in which the magnetic field might not be that high. You need microgauss, milligauss, but they are so large, up to 100 parsecs, that you could still actually explain many of these gamma ray radiation that we see by looking at these guys. So let me go back to my galactic outflows, my sky in the TV, and I want to just show what are the sources that we actually see. So I'm focusing here in this region, which is where the Vela supernova remnant. This is again an image of Rosita, and I chose it because you here have most of the two populations that we have the largest number of gamma rays, and this is supernova remnants. We have the Vela supernova remnants. This is Vela Junior and the Puppis A. And we also have the pulsar wind nebula. We have a bright pulsar, which is Vela, with a very bright pulsar wind nebulae, which is this blue thing, all these blue lines that you see here. This is the high energy emission in X-rays. So this high energy emission tells you what we can see actually in gamma rays. And we indeed look at these things, and then we see a lot of shell-like supernova remnants, like this guy, in which we actually can distinguish the morphology of the remnant and see the shock and how the particles are accelerated here and producing gamma rays. And we also see pulsar wind nebula. This is an image of this region obtained by the Hess telescope. So even if we look at this region very carefully with deep observations, then we have here Chandra, the pulsar, which is around here. This is an image of the Chandra, of the Chandra telescope in the Vela pulsar. And when we look carefully to this guy, we actually see a point-like source on top of the pulsar. And we do the timing analysis of these photons, and then we fold it with the period of the pulsar. We see that the photons come at the right rotational phase. So we actually know that there's also gamma rays about 5 TeV coming from the pulsar itself. But this is not the only things that we see. As I said, this is very rich right now. We have many things. We have microquasar. This is the case of SS43, which is a galactic black hole in which we see actually the jets, these ultra-relativistic jets. We also see non-relativistic shock besides supernova remnants, and we had the detection of the first novae, RS of Euclid, a couple of years ago. And then we see in general many objects or many populations that has to do with massive stars with fast winds. And this is either stars in compact objects, in binary systems with compact objects, or two stars together, or a group of stars in the collective effect of the wind and creating a big bubble and filling up with high energy particles. So how do we create how these shocks actually produce gamma rays? This is in the TeV regime, there's basically two kind of competing mechanisms. You have the acceleration here, somewhere in the shock, and you can accelerate electrons and you can accelerate protons or heavier nuclei. So if there is electrons, you basically, in the presence of magnetic field, you're going to have synchrotron radiation in the low energy band, and these high energy electrons will upscatter in photons to high energies and appear in the inverse. And that's why for us it's really important to have multi-wavelength observation on this, on all the wavebands to understand what's actually happening in the source. You can also have protons or hadrons, and then we have proton-proton interactions. You have protons accelerated in the shocks, and then you have some matter, some clouds there, and these protons, they interact inelastically with this matter and produce pions, and these pions, they decay, the neutral pions decay in gamma-gamma, and then you will have something as gamma rays at the level between GeV and MeV and TeV. How do we detect these gamma rays? Well, fortunately, this high radiation is filtered by the atmosphere. So basically, if you want to detect these gamma rays, we have to go up in the atmosphere, and then you basically put in your satellite, put a tracker and a calorimeter, and you detect the gamma rays, and then the photon, and you collect it and digitalize and so on. But when we go to the very high energies, and this is the TeV, it's really difficult, it gets really expensive to put this tracker on space. So what do we actually do is we use the atmosphere as a part of our detector. So here, then you have the same thing, but the atmosphere will be our tracker and calorimeter. So you have the photon coming into the atmosphere, producing an electromagnetic shower. Basically, the photon falls and creates a pair of electrons, positrons, and you create a shower of particles. So we basically can, to detect these particles that are falling onto us in a big area, basically what we do, these particles, when they travel faster than the speed of the light in the medium, in this case the air, then they produce a fast flash of Cherenkov radiation, which is ultraviolet light and is very, very thin. It's a nanosecond. So you need an array of big mirrors, arrays of telescopes with large mirrors. You focus this ultraviolet light on fast cameras, and you get your signal. So this is very effective, and then which is what we call the imaging atmospheric Cherenkov telescopes. But you can have the same different technique if the particles, if the photon is really energetic, the particles can actually reach the ground. And then there you can put some water. Instead of using the Cherenkov light on the air, you produce the Cherenkov light on water. And then you have that kind of tanks full with water, and you can just observe these very high energies like this, or using or detecting directly the electrons and positons and charged particles with scintillators. So this is what we have right now around the world. We have three big installation, array of telescopes. They are similar, they are all very powerful instruments. They have different configurations, depends, some of them, they are more focused on low energies, more in the high energies. In the north, we have MAGIC, that you probably know very well because it's in La Palma, and we have Veritas in North America, and we have HES, which is in the south hemisphere. And right now, we have the first prototype, LST-1, of the CTO observatory. And I'll speak about this in a couple of minutes. But I just want to also mention these two big experiments which are in Mexico, in HAWK, which is this water Cherenkov telescope, and LASSO, which is an hybrid, and they're producing really, really interesting results for above 100 TeV. So in the TV regime, I just want to focus on these three guys because we have a lot of results, a lot of cool things to show, but this is three things that I want to speak, and basically the ultra-relativistic outflows and relativistic outflows. So let me start with pulsars or with neutron stars, and we already heard a lot of pulsars yesterday, and magnetosphere just by Beatriz, so I got to just not explain that how a pulsar works. So basically, you have a very magnetized rotating star with an extremely high magnetic field, but you can produce photons at several places within this magnetosphere, so kind of everything is frozen there. You have some kind of gaps, you accelerate electrons, positrons, and then you produce this pulse emission. You could have potentially pulse emission in the ultra-relativistic wind. This is where this kind of sheet that she was also showing in a different scale of magnetic field, but you have this ultra-relativistic wind, which might also be stripped because of the movement of the pulsar, and then you also might get some pulsation there, or the nebula, but the nebula you would expect some steady emission in phase approximation. And indeed, these pulsars are really, really efficient in producing gamma rays. Here, I put again the sky by LAT, and then you see the three of the brightest source in the LAT sky are actually pulsar. This is the Minga pulsar, Crab, and Vela. And the emission is so high that goes on top of this fog that I showed before. But those are the only ones. LAT has actually detected many of them, and it's a very rich phenomenology, and the data set of the LAT right now is amazing. But for us TV astronomers, there is a bit of a problem. When you look at the spectrum, this is the energy spectrum, this is the typical synchrocurvature radiation because it's a magnetic field, very high magnetic field, but when you get to a few GeV, there is a very drastic drop-off of the flux. And this is the typical sensitivity for Cherenkov telescope. So it makes it really difficult for us to study pulsars. But we still, anyways, want to continue trying to get the signal from these guys. And we have 4 detections of pulsars. This 1706, Vela, Geminga, and Crab. And when we look at the spectrum, there comes a lot of surprises. First of all, we start seeing tails. And when tails mean this is, again, the Fermi emission, when you expect it to go down, but what we actually see is that it doesn't go down, but it continues to high energy with a power law. So something is happening there which we don't actually understand, and it doesn't really follow the kind of physics, simple physics we think it is. And even in the case of Vela, which is this guy here, what we see is that it's not just going down, but then you have a new component which reaches up to 20 tera-electron volts. So, and when we do the light curve, as I spoke before, this is again Fermi. So this is a HES in the low energy, but the high energy, this is beyond 5 TeV. And we see the emission is focused here in the rotational period of the P2, and it really reaches very, very, very high energies. So how do we explain this? It's very difficult. There's not a simple answer to this problem. We know this is what we measured with HES, these colored bands. This is, again, the points by Fermi. And then what we know is this has to be inverse quantum. There is no way around. And it has to be, for that, to reach 20 TeV, you need to get something like 4.10⁷ Lorentz factors in particles. So to get this, you can say, okay, let's just compare, and because they have the same rotational light curve, then we can just say, okay, let's just assume that the same electrons are responsible of this part and of this part. So you can assume this is curvature radiation, which is the standard interpretation. You have curvature radiation within the magnetosphere, and then would be the inverse quantum. But then when we look at this and we try to fit the TV data, we actually short. We don't really reach, and to actually reach this energy, we need to get this kind of gaps in which the particles are accelerated beyond the magnetosphere. So you have to go at least 20 times the light cylinder, which is the size of the magnetosphere, to really explain this. So this is still to be really understand what's going on here. We can also say, okay, this happens outside the magnetosphere, then you have this kind of strip wind, and then you have synchrotron radiation, then the magnetic field can be much reduced. I do synchrotron radiation here, and inverse quantum, but then you're even shorter. This is kind of solved if we think that something that you have a wind, which is ultra-relativistic, and it's got a gamma of around 5, but then again, you have to go a bit far away, too far maybe to explain the light curve. So this is something of an open problem that we're still working and trying to find more about it. Another compact object with outflows, with relativistic outflows, is this famous Manatee Nebula, SS433. We had the black hole here. And the black hole has this kind of the jets which are precessing up to 0.1 parsecs, then they kind of disappear, and they reappear later around 25 parsecs. And this is when you see these huge outflows which fill up all this nebula up to 100 parsecs. So we actually look at this guy for around 100 hours, and this is, again, the nebula in radio and low wavelengths, and the X-rays, this is here you have the black hole from which we don't see emission, and this is the hard X-rays. And what we actually see, when we look at the emission, the gamma ray emission at different energy bands, is that you have the maximum of energy in the shock, when the jets reappeared, and then the emission goes down. So basically, the high energy emission, the photons are closer to the black hole. And this is actually understood as there is something, basically the jets are launched with 1/4 of the speed of light, and then they reach something, and this is like an electron trap. You just trap them there and make it slow, and we could just model this and get a velocity of 0.08, and then this is where all the particles are accelerated, and in this to create this shock, and then this electron should be accelerated at least to 200 TeV. So that is the first time that we detect a microquasar. And the most interesting thing is it tells you how efficient these guys are also to accelerate and produce gamma rays. And there are actually several of them coming up in the summit conference. The last example I want to show is the Novi. Novi are nuclear explosion. You have like a compact object, so a white dwarf, and with some bright, big red giant star, which is accreting, which is accreting matter over the white dwarf until the pressure is too high, and then you have a nuclear explosion. And this nuclear explosion produces a huge shock very fast. You can reach velocities between 400 and 5,000 kilometers per second, and the kinetic energy is also high enough. Those guys have been detected up to now by Fermi with GeV satellites, but they were never detected, and they were not really thought to be so energetic to produce TeV gamma rays. So we look at this guy, RSOFUKIS, which actually went upwards. This is like the historical light curve of RSOF since 1930, and we look at it in the outburst from happens in the middle of August in a couple of years ago in 2021. We saw an alert from Fermi with a very high ejecta velocity of 2,600 kilometers per second with very bright, and then we look at this guy and we actually detect it. And we saw a very interesting behavior. This is basically the light curve, the energy flux over time. So this is where we got the trigger, and then Fermi went up at the maximum and then went down, declined, the flux declined. And what we actually saw is the flux goes up a couple of days later, and then you have the maximum, and then it goes down up to, this is what time that we couldn't observe, we re-observe later, and it actually follows the same trend that we saw in LAT. So basically, this is what is happening. There are just 2 days, in 9th of August and the 13th of August in orange. We basically say is the high energy in the GB regime, that you have the peak, and which you can observe here, and then as the day passes, the emission in the GB goes down, but it becomes harder at the high energy. And this is, we believe it is because the hadrons, the protons, they need some time to actually reach the maximum energy that we see, which is around 10 TeV in protons. And this is it's the first time that we detect these guys, and these probably protons, and then we also can prove there is acceleration of protons of this guy up to 10% efficiency, which is pretty high for this kind of shocks. And that also tells us a lot how a shock behaves. We always study shocks in supernova remnant, but here for the first time we could see a shock evolution in real time. So, and something very also interesting that I didn't say is that's what detected. Everyone was looking at it, MAGIC, MAGIC and HES, but also the LST1 was looking at it, and they actually detected. It's a very nice result, and this is the result by the LST1, and the LST1 is the first prototype that we have in La Palma as part of the Cherenkov Telescope Array Observatory. So this is a beautiful instrument, and it's located now in La Palma. This is which is as a part of this observatory, which we foresee. So we are building it right now. We have one site in the north in La Palma, which will have four of these large-size telescopes and 9 of the MST telescopes. And then we have another one in the south, near Paranal, in which we will have different MSTs and in a larger array, what we call the SSTs, which is a small-sized telescope. And this configuration has to do with the kind of energy in which you want to actually focus. This could be more in the extragalactic light, just in the lower energies, in decreasing the energy threshold, and this guy would be more for galactic science, and just looking into the PV sky. And for that, we said we use these 3 types of telescope, the LSTs, which have 45 meters, the MSTs, which with 27 meters, and the small-sized telescopes, which are not that small, they are 9 meters. So this is a photo that they sent me a couple of weeks ago. This is how it looks right now in La Palma. This is the LST1, but the LST2, 3, and 4, they're already being built right now. So, this, by next year, we hope to have everything ready, including probably the starting construction of the first MST. And there is also a large Spanish contribution. And this is really important, I think, for the Spanish community to know that we have this fantastic instrument, which will be, as I said, the most sensitive Cherenkov instrument in the world by 2025. There's been a lot of contributions here these days, and also tomorrow. There's been first science with LST and some general one, and transient TV astronomy by Paul and Alicia. And this is a lot of galactic contribution. There's already from the LST taking data and getting very, very high quality results on novae, on pulsars, on protostar, pivotron, massive stellar clusters. And also, if you're interested in extragalactic science, this is a fantastic instrument for extragalactic science, for following BLX, quasars, and blazars, and you can just look at this contribution here. And something that I want to just mention, this is the access to the CTAO data. So this is thought we want to have an open observatory. That means a proposal-driven observatory in which 37% will be open time, but the host countries will get 20% guaranteed time. And actually, we are the host, one of the host countries. So that gives us really a great opportunity to do multi-wavelength observation, to work with us, and to get the best out of and exploit and get the best out of this instrument. This is just a glimpse of what we expect to observe when you do galactic science. This is the result we get with HES. Here is the galactic latitude and galactic longitude. The galactic center is here, and this is the region I showed you before from the Vela Junior and Vela X, and this is all the sources that we see right now. But with CTA, we expect to see something like that, and this is really a wealth of new physics and new data that we expect to detect with the CTA. So I get to my final remarks. I hope I convinced you that we are really we are not particle physics anymore, but we are right now doing kind of astrophysics, and I'm convinced in the next years, CTA will be bringing most of the interesting results in the field, on the field of astrophysics. And just let me emphasize again, the north side will be in La Palma, so let's use it. Thank you very much.
Okay, thanks a lot, Emma. It was a very nice talk. We have some time for questions. Who wants to be the first? Yeah. Okay, I have a question. Yeah, referring to SS433, that is very impressive. The image. I mean, it's not a very particular micro-quasar, in fact, because it's not ultra-relativistic. The velocities that you have reported are between 0.25 z and even 0.1 z, more or less. In fact, my question relates to the fact: do you see any kind of relativistic effect in the position of the knots when you compare West 1 or East 1, the knots that are at the eastern side or the western side? There is a correspondence between 1 1 and 2 and 2. I don't see. Let me ask you whether there are some differences between these knots.
No, actually, we don't see much difference between the two sides. We see the two sides, but the velocities that we can infer, they are actually pretty similar. So we are re-observing now, and I see Veritas is also re-observing. We're trying to put everything together to see if we can just get. But of course, this is a weak source for us. Yeah. We detect it after 100 hours, which takes 100 hours. So, and it's very, very close to a very bright source, but we didn't see many difference between the two sides. But this is a very interesting effect indeed. Okay, thanks.
So, thanks, Emma. I have a question on the acceleration of particles. So now that you show that also novae and all these pulsar wind nebulae can also accelerate, has it changed our picture that supernova remnants are the main cosmic ray accelerators in the universe or in the galaxy? Could you comment on that?
You are not the right person to answer because I don't believe these supernovas are sources of cosmic rays.
Okay, so I would like to know your opinion.
I think it's more clear that supernova remnants, they are indeed the source of the bulk of cosmic rays. They are the most efficient way to accelerate cosmic rays, heavy cosmic rays in the GeV. Then when you go into the PeV regime, we don't see many of the supernovae reaching these high energies. And then we start to see a lot of new population of sources which are actually PeV emitters, which are not supernova remnants. It doesn't mean those guys, they might be one or two, but I think the general idea right now is that you might have contribution of different population of galactic sources to the cosmic rays, here, including stellar clusters and winds of massive stars.
Okay, so which comes to my second question. How long will it take the CTAO to take a really very deep, let's say 1 order of magnitude deeper than current surveys of the galactic planes and search for all these cosmic ray accelerators to maybe do population synthesis and come to an answer? Do you have, well, the CTA has some estimates or ideas?
You mean how long will it take to have an answer to this kind of
question? No, I mean, how many, let's put it, how many years will it take to do a deep survey that will go, let's say, one order of magnitude below what the current sensitivity is?
I think, well, to get a survey, our plan, I mean, for next year already, this site will be more sensitive than everything that is around. We still need some time to build the one in the south, which is when we're going to do the survey. But the survey, basically, we have like 10 years, 3 years that we expect to devote just for the survey, and there we should have like way more sensitive than, 10 times more sensitive than what it has done in 10 years.
Thanks.
Okay, just one last question.
One quick question. Is there any project ongoing or planned to have like an extragalactic survey in the zone of avoidance with these instruments?
Yeah, I mean, there is something maybe I didn't mention, but it's interesting to say. We, as a collaboration, we have what we call the the key science projects. The key science projects is 40% is for in-kind contribution from people who are building the telescope, and we have science projects which are what we consider key, or this is kind of for the community, for the astrophysics, they need the expertise of the community. One of these key science projects is indeed an extragalactic survey. So it's to get 1/4 of the sky and do kind of, not shallow, maybe shallower than the galactic plane, but really look into to do a census of the extragalactic part of the sky.
I mean, specifically in the zone of avoidance where we have a problem with the ground-based telescopes.
We're going to have one array on the south and one array on the north. So in principle, we should be able to cover the north and south hemisphere.
Okay, thanks, Emma. Thanks a lot for your talk. Okay, and we move to a completely different field. It's galaxy formation simulations in the exascale computing era. And the speaker is Claudio Dalla Vecchia from IEC. Okay, I will let you know after 23 minutes, okay?
Hi everyone, and thank you to the organizers for inviting me. So I was asked to talk about this specific technical topic. I will try to make it a bit more accessible than what it sounds in the title. Starting with the definition, exascale computing area is basically the next generation of supercomputers that will be able to run at exaflops speed. And one exaflop is 10 to the 18 floating point operation per second. So just to put it in human terms, is what, I mean, your laptop to do a second of computation, comparable to this, would take something like 100,000 years, and these computers can do it in 1 year. So, but I come from mostly galaxy formation and the development of models for galaxy formation. And before continuing to the topic, I would like to point you at this article that Gustavo Yepes and I wrote for the Boletín de la SEA, the last issue, which is about the computational astrophysics in Spain, its evolution since the installation of the first supercomputers in the Barcelona Supercomputing Center. What is the connection with the European strategy for supercomputing, and what are the challenges for the future, right? So it's a pretty long article, but I mean, if you dare to read it, it's a good read. So, as a general introduction for, so why do we do galaxy formation simulations? What is the motivation? And I think the main motivation is that observations can observe a lot of galaxies, and but they are like frozen in time, right? So you see a galaxy, and you don't know anything about its evolution. I mean, you can infer from properties of the galaxy what happened in the past, but you don't see its evolution. You see just a picture. It's like taking a picture of a 30-year-old person. They give you a picture, you see the picture, you infer, well, it should be 30-year-old, but you don't know how this person was when she or he was a kid, and you don't know how it will evolve later. You can guess that because you see galaxies at different times in the universe, at different times of their evolution, but you don't see the same galaxy at different times of their evolution. So what a simulation can give is following the evolution time of the assembly of galaxy, of each galaxy that you have in your volume. So we talk mostly about simulation cosmological volumes that are used basically for comparing the properties of galaxy populations, like observed by large surveys. There are other type of simulations, zoom-in simulation, maybe you know a bit about them, that focus more on single objects or their satellites, the Milky Way, or a dwarf galaxy, or a cluster of galaxy, but just single objects. They are both cosmological, but these are volumes that are filled of galaxy everywhere, right? And going on, just a very brief summary of what these simulations are. So these are volumes, periodic volumes, cubes of this size. This is from the TNG, a nice illustration from the TNG, latest TNG simulation. And they can have different sizes, right? So right now, more or less, what is used as a good compromise between volume size and the resolution, this is the resolution, is around 100 megaparsec. Resolution, spatial resolution is around half kiloparsec. Gas mass resolution is around 10 to the 5, 10 to the 6 solar mass. That translates also in stellar mass that can be resolved, and dark matter mass is about this. Okay, there are already efforts to go beyond that, but let's take this as an example. And what does it mean if we wanted to simulate, for example, a larger number of clusters? We would need to go to a much larger volume and to sacrifice a bit the resolution, normally, to be able to run it in a time that is comparable to the time this simulation has been run. We can also go to much smaller scales and try to go on smaller, to resolve smaller galaxies, and this usually is done by decreasing the size of the volume, maintaining the same number of particles, increasing the resolution, and taking more or less the same time of this, right? So this is a bit the idea, the basic idea. It's not all like this, but if you go to larger volume, the resolution decreases, right? So this is a list of things that are now basically in all codes, maybe the last two no, but all codes that are modeling galaxy evolution have to take into account gravity for sure, because it's the driver of structure formation, hydrodynamics to describe the thermodynamical state of the baryonic gas, gas cooling, which is also a very important thing, especially connected to chemical enrichment of the gas, and line cooling and molecular cooling, star formation, which is driven by gas cooling, and then all what we put in a big, under the big umbrella of feedback, which is anything that is returned to the gas phase, in form of energy, in form of chemical enrichment, in form of non-thermal pressure from magnetic field, cosmic rays, or in form of radiation for the few simulations that are able also to follow radiative transport, right? So all these, each one of these would need at least one talk or two each to be explained. But I mean, there are a couple of very interesting reviews that you can find in the last years that came out, and I was, yes, it was interesting to see that the word challenges appears 2 or 3 times, and this is a sign that the field is really young. People expect from simulation amazing things, but it's 30 years, more or less, that we are able to do galaxy formation with numerical simulation. So just to go back to what is the resolution and the need of resolution, this is a quite old plot, but it's very illustrative. This is star formation rate density, so it's the star formation rate per unit volume in one of these simulation, cosmological simulation, as function of redshift or time. And the points are observations. These are pretty old recopilation of observation. Now, we know that JWST is putting points here on this side, quite high star formation density at high redshift. But this is the effect of resolution. Resolution increases in the simulation. These are simulated star formation density, star formation histories coming from this from the evolution of galaxy in these volumes, and the resolution increases this way. So you can see that increasing resolution, the onset of star formation is at earlier time or later or higher redshift. You can see the same thing here. This is what we call merger tree, and it's a picture of the assembly of the mass of one main galaxy, which is moving on this line. Color is of the points is the stellar mass, and time is going from the bottom here up here. So this is redshift 0, and this is redshift 10. And here you can see, you can reconstruct all the mass assembly and where all the mass, stellar mass that ended up in this galaxy came from, right? There is stellar mass produced in situ, and then there are mergers with satellites. And you can see that the first satellites here that are, around this mass, so the limit of the resolution of the simulation I showed you before are formed around redshift 10(9), right? So this is very interesting because these simulations were expected to explain JWST finding, but it's very clear that we have to go to larger, higher resolution to be able to get galaxy forming a bit earlier and the onset of star formation a bit earlier. Curiously, if you look at this envelope, it goes like this. So the expectation is that it goes through what is observed with JWST. And the other thing that is needed is a larger volume. At high redshift, first galaxy form on the higher density regions, the higher overdensities, and to be able to capture these galaxies that are forming earlier than other, the volume of 100 megaparsec may be too small. So one should go to larger volume and higher density, which is the challenge of all the simulation or the models we are running. So this shows where we are right now, more or less. This is a list of simulations. These are the dark symbols are all hydrodynamic simulations of volumes that produce galaxies. And this is the open symbols are all dark matter simulation, so only gravity. Here you have on the x-axis the box size of the simulation, and on the y-axis the mass, or let's say the resolution of the dark matter particle. Higher resolution is on the bottom, right? And these lines that you see here tells how many particles are in each volume, for each volume at a given dark matter mass. And you can see we are here with the hydrodynamic simulation, a bit better and larger volume with M-body simulation. So the idea is to move perpendicular to these lines, increasing resolution and increasing box size with time. Okay, so this needs more computer power, which is what I'm going to talk now. Needs for numerical code able to scale on a very large number of cores, which is a very challenging thing. And that depends on memory and load balancing that the code have to solve, especially load balancing. So being able to distribute the workload, the calculation on 100,000 cores and not having 10 cores running calculation while all the others are waiting. This is a very challenging thing to do, and there are some solutions. But before going to the solution, this is what we are now planning at European level with the Euro-HPC joint undertaking, which is an initiative of EU countries and companies, right, to develop a supercomputing ecosystem in Europe. It's the substitute of PRAISE, what was the previous consortium financing supercomputer. The plan is to install these exaflops capable supercomputer, and 3 pre-exascale supercomputers have been approved and installed, and they are now running, and I will show you what they are. And then the interesting thing is that machine learning, artificial intelligence move towards the architecture using GPUs, right? So GPUs are very, very efficient for machine learning, artificial intelligence. So now all these supercomputers to achieve this extraordinary compute power are using GPU. GPU have another important properties that they can do much more computation for much less, using much less energy than normal CPUs. So they are also more efficient energy-wise. So the three computers that have been approved and installed are these: Lumi in Finland, Leonardo in Italy, Mare Nostrum in Spain, at the BSc. Lumi has a capacity of more than 500 petaflops, so half an exaflop, and Leonardo and Mare Nostrum around 300 petaflops, right? So So just a quick summary of the characteristic of Mare Nostrum. There are 2 partitions, well, there are 3 partitions, there are 4 partitions, depending on the day you look at the website. These things are added every day, but there is a general purpose partition with the 718,000 cores. It's just a CPU based. And then the accelerated partition that has almost 4,500 GPUs installed. And then general purpose, this is already looking forward in time, the new NVIDIA Grace CPU that are ARM CPU with GPU included in the same chip. And then there is a next one that on the website they say, well, we cannot say yet. Okay, so these are installations that are done for testing new hardware and the possibility of installing next supercomputer using this hardware. One of the challenges of all this is that GPU-based computers can have GPUs of different vendors. So Lumi has GPU from AMD, Leonardo and Mare Nostrum from CUDA, and they are not compatible. So there is still a big problem, big challenge is the compatibility. There is not a real standard, so each vendor has its own compiler, its own libraries, etc. CUDA from NVIDIA is the most used, so we are on the safe side, at least here in Spain. But it would be almost, very difficult to change a code to put it on this supercomputer in Finland. It's a lot of time to do that. Talking about public numerical codes, and here I'm only talking about codes that have a full galaxy formation model, right? Already in things. And these are 3 very advanced codes. One is Swift, which is task-based, use task-based parallelism, and it's a way to overcome the problem of load balancing I was telling before by breaking in tasks that are studying the interconnection between different tasks, the calculation, right, and distribute that through a library through cores, and keeping all the cores busy in doing calculations, so there is no wasted time. Changa uses a similar thing using the Charm++ library, mostly for dynamic load balancing, which is what I was talking here, more or less. But they also support for GPU, so it's already on the side of the new supercomputer that I installed. And PKD Graph is an MPI multi-threading and GPU-based embodied code. And I say embodied, and some of you know PKD Graph because they are in Euclid. The Euclid flagship simulation was run with this code, and the volume, this is embodied, so only gravity volume was containing 2,000 billion particles, right? So it's one of the largest simulation ever run, embodied simulation. It was run on 4,000 GPUs on Pittsnight, which is a supercomputer of the National Supercomputing Facility in Switzerland, and it took 8 hours, so a bit more than 3 days. So it's a very, very well-optimized code. But as I say, it's embodied. So why I put it in the list of codes with galaxy formation models? Because we are at the ISC, we are working on that. So in collaboration with Douglas Potter and Joachim Steidel, who are the main developers of PKD Graph, we had an agreement with them that we were adding hydrodynamics solver galaxy formation model. For now is based on the Eagle simulation, but it can be whatever. And we are starting to put in relativity transfer. So they were very happy to collaborate with us. Everything we are producing goes in the public version of PKD Graph 3, right? I'm not saying go and use it because there are still some things to fix in the code, but we are at a good point after 6 years of development to have the code ready for running. And lately, we expanded the collaboration with Jose Antonio Pascual and his students They are from San Sebastian. They are engineers, and they were looking for an application for GPUs. And so they offered to do a porting of the hydrodynamics to GPU. So we start to have already gravity and the embodied part, hydrodynamics on GPU, and later I hope, the relativity transfer on GPU. So the good thing is that, PKD Gravity is released under open source license, and we kept everything under open source license. So everything we put in the code is available for free, basically. So in summary, I gave a brief introduction to cosmological simulation, motivated the need for large volume and higher resolution. You have seen this. I gave an example with a high redshift universe, but there are large surveys, if you think of, for example, Euclid, that are observing a lot of emitting line galaxies. So these, are large volumes that needs sufficiently high resolution to account for all the galaxies that are observed by this survey. The European effort, is to provide exascale computing infrastructure, and then, it's mostly motivated by machine learning and artificial intelligence, but we can take advantage of that. And there are many other applications, not only in astrophysics, that can take advantage of this kind of infrastructure. So we are on a good side here. There is a lot of money put there. There is a lot of effort, mostly because of the people are scared of AI. So Europe wants to be at the forefront also in this. And for us, it's a good thing. And there are only a handful of modern cosmological codes, as I say, that can be efficiently used, but there will be more coming. For sure, there will be more coming. Developing this kind of codes takes years, right? So, only a few years ago, it wasn't really clear what kind of architecture were going to be used for the next generation of supercomputers. GPU were not the most appreciated for the problem I said of compatibility and standard. But then thanks to artificial intelligence, now we have that. And that is all.
Okay, thanks, Claudio. Okay, we'll have time for questions. There, please.
Could you comment on how do you expect that the new generation of numerical simulations is going to solve the apparent tension between the number of galaxies, a very high redshift that the James Webb seems to be observing, which was the motivation of all the talk. So are you going to solve the problem, what the problems are the problems in the code? Could you comment on that?
Yes, I don't know. Maybe there is some physics missing. Maybe the model needs some adjustment. But this points to the really points to the, how can I say? It points to the fact that the problem may be only resolution in the current simulations. So when you try to compare high redshift observations, you don't have a simulation that can reproduce those high redshift simulations. You are not in the regime for this kind of simulation. Is that the question? Because I kind of.
So going a bit further in this question, it seems to me that the observers, every time we put a new telescope on the sky, it seems that it surprises, the universe surprises us, and the evolution seems to be much quicker than what we expected based on these simulations. You're putting all the emphasis on the resolution, but there should be some physics behind that continuous surprise of the universe to our eyes. Maybe some missing dark matter properties, maybe primordial black holes, but it seems to be that there should be some physical reason, not just technical limitations of our computers.
So one thing, I mean, there could be. I'm not saying that there cannot be. What I think is that from one side, we should wait a bit more to have more statistics from these high redshift observations and see, because I mean, some of these points that you see here moved a lot with more observations. If you look at this plot now, this is much thinner. There's much less scatter here and much less scatter here and many more points here. So in part, I would like to see more data from the high redshift universe to see the thing. Then I'm a bit worried that there is a bias in the observations, because when you observe the most luminous objects, right, the bias could be that they are forming in the highest density regions. And highest density regions, the evolution is faster, right? It's generally faster. So galaxy evolves a bit faster than, for example, at the average density of the universe or in a void. So that's why it would be interesting to have more volume, more objects, and try to see if then something changed. But I agree with you. There could be more either need of better modeling of the physics that we know. Going to say that maybe we need more physics or different. This I don't know, right? But it's a possibility.
Yeah, I would like to know your opinion on how long it will take for quantum computing to replace this binary-based GPU computing. 10 years, 20 years, a little more than that, less than that?
I don't have an opinion. I would say on the order of 10 years, right? But I mean, these things, if you just look at how machine learning from nothing became grow exponentially, I don't see why quantum computing cannot resolve some of the challenging problems, technical problems that it has, and just explode in the next few years. But I would say that 10 years. It's challenging. It's challenging, I mean, technically, to keep processors at 4 millikelvin.
Any other questions? Okay. Thanks a lot for the last one. It was going to be my question also. Then. Okay, good. Then let's thank again the speakers this afternoon, Beatriz, Emma, and Claudio. And let's wish the fourth speaker, Miliana, a quick recovery. Okay, we go for coffee. She's, what? She's recovering, okay. Then let's go for coffee, and then we should be back at, I don't know exactly the time. Okay, should be I think it's 5:45. Okay, see you, bye.